Dear students, I am very glad that you decided to start my course, so very welcome to my first lecture. I am planning, first of all, to give you some motivations for the theory of Jacobi form. So the title of the first section, Motivations. The plan of the first section is the following. First of all, I would like to analyze the arithmetic generating function. So, generating functions for the arithmetic problem of the representation of numbers by quadratic form. Then we consider partition function of the same problem. After that, I would like to give you the definition of the classical modular form in one variable. And after that, we construct an elliptization of the famous Ramanujan delta function. So elliptization of the Ramanujan delta function, delta in tau. More exactly, I construct here an elliptization of some infinite product. Let me start by the first definition. This is the definition of the lattice, because I would like to construct the generating function of a quadratic lattice. So let L be an integral even, positive definite, quadratic, lattice. What is it? First of all, a lattice. This means that L is a free Z module of rank n. So L is isomorphic as integral module to Z to the power n. Then integral quadratic. It means then there is a symmetric bilinear pairing defined on the direct product of L with integral value. In other words, we have here an integral quadratic form. Even, what is it? It means that the norm of any vector in L is even for any V in L. And the last property, which is more or less evident, positive definite means that for any non-zero v in L, its scalar square is strictly positive. This is the object which we would like to work with. So let me repeat, L, B, an even integral positive definite quadratic lattice of rank n. Here, certainly, we assume that n is strictly positive. So now I would like to define generating function for this lattice. Or in another word, the theta function of this lattice. Let's consider the following arithmetic question. I denote by R, L, 2n the number of vectors in L of the fixed scalar square 2n. I use here 2n because the lattice is even. Moreover, the lattice is positive definite, therefore this number is finite. Now we can construct the generating function for this quantity, or we can define the theta function of the lattice L. This is the following formal sum. R, L, 2n, q to the power n. And we have the summation over all non-negative integral n. Certainly the first term of this generating function is 1. Because the lattice is positive definite. This is a formal function. But now I would like to construct a holomorphic function related to this generating function. We put q equal to the e to the power 2 pi I tau, where tau is a point in the so-called upper half plane. This is the set of complex numbers with positive definite imaginary part. And we have the following expression for the same generating function. E to the power p I v to the square tau. The summation is taken over all v in L. Another notation for the same function is theta L tau. This function is holomorphic on the upper half plane. Moreover, how to understand this transformation from tau to q? So tau is element from the upper half plane. And Q is an element of the unit disk. Because the absolute value of Q is equal to e to the power minus pi y, strictly less than 1. What do we have here at 0? This is the image of the infinite point E infinity of the upper half plane. So we can treat the same function, the same generating function, as a function on the unit open disk, or as a function in the variable tau on the upper half plane.